Stig Larsson from Chambers University of Technology, and he'll be talking about finite element approximation of the Cahn-Hilliard-Cook equation.
Thank you very much. I'm also very grateful that I was given the opportunity to take part in this and to speak to you. With my background in numerical PDEs, not stochastic mathematics, I guess I should feel like an outsider here, but in fact I don't, because I have met so many interesting people and made good friends in the SPDE communities, so I feel quite at home. I will talk about our work, which is about finite element approximation of stochastic PDEs, and I will emphasize the Cahn-Hilliard-Cook equation. That will be the like a running thread in this presentation. So this is the Cahn-Hilliard equation, which we have heard about earlier. Ludovic Goudnèche gave a good introduction to the Cahn-Hilliard equation, and it's perturbed by noise. This is often called the Cahn-Hilliard-Cook equation. And so we are solving for two functions, u and v, and there are two PDEs. So we are solving for u of t and v of t, in a spatial domain D in 3 up to 3D. And there is a nonlinear term, which I take to be cubic, like this, the derivative of a double Weld potential. And we have Neumann boundary conditions for both the variables u and v. And there is an initial condition for u. And u is the order parameter, which is related to the concentration of the substances, components in a mixture. So my business is to prove convergence estimates for numerical approximations, and I will emphasize a spatial approximation by the finite element method in this talk. And in order to do so, I will put the equation in an abstract framework, and I'm of type B, so I will use the Prato-Sapchik-Rosovsky framework, and then I will discretize by finite elements in a standard way, and then I will, since this is an equation with additive noise, it's naturally splits into the linear equation and the nonlinear. So also the analysis splits like that. So for the linear Cahn-Hilliard-Cook equation, I will demonstrate strong convergence estimates and weak convergence estimates. And for the nonlinear equation, I will demonstrate strong convergences. So this is a joint work with Michi Kovac, who was here until yesterday, and Fredrik Lindgren, my student, who is here still, and Fadin Said Pana and Ali Meshfouroush are former students of mine. Okay, so we have this system of two PDEs perturbed by noise. We want to put it in the abstract framework of the Prato and Sapchik. So first we eliminate V so that we get only one equation, which will be of fourth order then, because we eliminate V from here and put here. And we let A be minus delta, the Neumann Laplacian, and that occurs both here and here. And we consider this as an unbounded operator on the Hilbert space H, which is L2 over the spatial domain. And I rename the unknown variable to be called x. And finally, W will be a Q-Wiener process on H with respect to a filtered probability space, so that we have the Hilbert space valued Ito integral. So now we can write the equation like this: dx plus a squared x plus a f of x dt equals dw. So the linear part of the operator here is a squared, and the nonlinear term is a, the Laplacian applied to f, where f is a cubic nonlinearity. Okay, an important ingredient in this framework is the semigroup generated by minus a squared. And so the Neumann Laplacian has a sequence of non-negative eigenvalues starting with 0, and we take an ON basis of eigenfunctions, and the first one is constant in space. And then we can define the semigroup generated by minus a squared. I often denote it by e of t, but we can also write e to the minus ta squared. Now it can be conveniently expressed in terms of the eigen pairs, lambda and phi. And here I note that the constant eigenmode is also constant in time. This will be a little important later, because constant functions can be exactly represented by the finite elements. Okay, so the semigroup is the solution operator of the linear homogeneous equation, where there is a 0 here, and it acts on the initial value. And if you have a non-homogeneous equation, you get this solution formula, which involves the convolution of the semigroup and f. Okay, so we return to the nonlinear Cahn-Hilliard-Cook equation, and we make sense of it in terms of a mild solution, which is this equation here, where we have here the initial value evolved by the semigroup. The nonlinear term, a f of x, is convolved with the semigroup. And here we have a stochastic convolution of the semigroup with dw. So the solution process x then naturally splits into two terms, y and wa, where wa is the stochastic convolution, and where the other part, this blue part here, satisfies a random evolution problem, where the we have a true time derivative here, and the nonlinear term is f of x, which is y plus wa. So we study these separately. Now we discretize by the finite element method. The finite element method is a Galerkin method, which is based on approximating subspaces consisting of piecewise polynomial functions. And so we take a family of triangulations of the spatial domain, denoted by th, parameterized by the mesh size h, which is supposed to go to 0, and corresponding finite element function spaces sh, consisting of continuous piecewise linear functions, polynomials of degree 1, or you could take higher degree also, but I will stick to this in this talk. They are subspaces of the true phase space for second order PDEs. And so we can write the finite element equations here in the original system of two PDEs. So we have we seek UH and VH by this Galerkin method with trial functions UH of t and VH of t, and test functions chi taken from the finite element space. So the Laplace operator here has been integrated by parts, as usual in the finite element method. So in order to, so this is how you would implement the method. Of course, you would have to do time stepping also, but I will not discuss that today. But that's how you would implement it. But we analyze it within the same framework, Hilbert space framework. So we introduce the operator AH, which acts on the finite element functions, the discrete Laplacian, which is defined like this. And that occurs here and here. And the orthogonal projector onto the finite element functions, which is defined like this. So that's going to be used here and here. And then I eliminate VH, and I end up with this operator equation in the finite element space SH. So I have AH squared here. I have AH PHF of XH, I forgot the H here. And the noise is projected. The initial value is also projected. There is also a semigroup generated by minus AH squared, which can be written down in terms of the eigen pairs. We have a sequence, now finite sequence of eigenvalues, starting with zeros and eigenfunctions, where the first one is constant. And so we get the finite element semigroup EH, or e to the minus t AH squared. So then for the finite element equation we also have the mild solution, which consists of the stochastic convolution WAH and a random evolution problem for the other part YH. So we will study these two separately. And I will begin with the stochastic convolution, which is the solution of this equation here, where there is no nonlinear term. So here x of t is WA of t, the stochastic convolution. And the first result that I want to present is about the regularity of this. So in order to measure the regularity, I introduce norms defined through the operator A. So the norm of order beta is the norm in H of a to the beta over 2 acting on V, or in terms of the eigenpairs, it can be written like this. Of course, this is only a semi-norm because it ignores the constant eigenmode. So if you add a term corresponding to the constant eigenmode, you get a norm which is essentially equivalent to the standard Sobolev norm of order beta. And I also denote by h dot beta the corresponding space. I also introduce mean square norms like this, where you take the expected value of the norm of order beta squared. Okay, then the regularity of the stochastic convolution, the spatial regularity, is of order beta, provided that the covariance operator Q satisfies this, namely that the operator a to the beta minus 2 over 2 times q to the 1/2 is Hilbert-Schmidt for some beta. So this condition here is a condition on how strongly smoothing the covariance operator is. The higher beta, the more smoothing Q has to be. And you get regularity, mean square regularity of order beta. Okay? The proof is rather simple. You just apply, you take norm here and apply Ito's isometry and use the smoothing effect of the semigroup. the smoothing effect accounts for the minus 2 here. Okay. Now let's discuss convergence of the finite element method. So we work in H, L2 over D. Let me also introduce H dot, which is the subspace of functions with 0 average. And then the orthogonal projector onto H dot. So if we then write the stochastic convolution and separate the constant eigenmode out using the projector, then the remaining part is just to integrate dw, and you get w. It's constant in space and like w in time. The same for the finite element approximation. It also has this constant eigenmode. So when you form the error between them, this cancels out, and you can work in this space. So we have here a convolution where we have the difference between the two semigroups here, which I denote by FH, and the P, the projector. So we have to study this, which is something about the approximation of the semigroup by the finite element method. Okay, so I want to study the difference between the two semigroups. And they solve these two homogeneous equations. So this is just a error analysis for the corresponding deterministic linear homogeneous Cahn-Hilliard equation. And for that, it has been known since earlier that pointwise in time you have an error estimate of order h to the beta if the initial value has regularity of order beta. This holds for beta between 0 and 2. The upper limit 2 is the highest order you can achieve for piecewise linear finite elements. For finite elements of higher degree, you would have a higher upper limit here. But we also need an error estimate which is mean square, which is L2 in time also. And for that you get the same rate of convergence, h to the beta, except for a logarithmic factor. But the regularity requirement is order 2 less. Here we have to start with beta equals 1, because when beta is 0, the regularity would be minus 2, which is too irregular to put in the finite element method. Okay, so this is an error estimate for the deterministic linear Cahn-Hilliard equation. And it's this work that I'm presenting, this is really the difficult part. It's surprisingly technical to prove this. For the heat equation, the corresponding error estimate of this form is very easy to prove. It's a 3-line proof, while this is more difficult. But here, for the Cahn-Hilliard, since we are solving two equations that are coupled, the error analysis becomes quite complicated. Okay, so then we can put that back into the stochastic equation. So under the same condition, this condition here, which gives regularity of order beta, we also get convergence of order beta for the stochastic convolution. And the proof is now quite simple. So you write the mean square of the error which is this, where we have the deterministic error operator here, and we apply Ito's isometry, so we get an integral of this Hilbert-Schmidt norm of fh and p q to the 1/2. And we compute the Hilbert-Schmidt norm using an arbitrary ON basis, phi j. And then we have here an integral in time of the square of the norm, which is what I had on the previous slide. And that converges with order h to the beta and the log factor. And it requires regularity of order beta minus 2 of the initial value, which is now this, which can then be interpreted as the Hilbert-Schmidt norm of a to the beta minus 2 over 2 q1/2. So the main technical work lies in the proof of an error estimate for the deterministic problem. So this is from this recent paper of with my student Ali Mesrouche. And we also consider Euler time stepping and obtain similar results. Now, this type of proof was, I think, first used by Printemps, where he studied time stepping only, and then for the heat equation. And my student, Yubin Yen, studied space discretization for the heat equation. In other work, we have also done a similar analysis for the wave equation. And there is also other by Martha Sanz and Louis Kerr, similar results, but with different proof techniques. Okay. Now I will discuss weak error estimates. So strong error means that we estimate the error in a mean square norm like this. That's what I did. And now we will talk about weak error, where we look at the expected value of some function of the solution at some time for some class of functions, G, real valued, defined on the Hilbert space. And in order to do this, I will present an error representation formula for the weak error. And in order to do so, I consider a more general evolution equation like this, with the linear term ax and b dw here. So the mild solution then looks like this. And if we apply an integrating factor to this, which is e to the capital T minus t, if we apply that to here, then the left side will be an exact differential, and I rename the solution to y here. So we get a new function y of t, which is given by this. Now, this formula here and that they coincide at the final time capital T. So we might as well use this one. But the point is that there is no drift term in the equation for y. And then we can do the same for the finite element approximations. Okay? And more generally, I look at an auxiliary problem where I have of the same form, but where I have an arbitrary initial time tau and initial value xc. And then I can define a function u from the Hilbert space and the time interval with real values by taking the expected value of the test function g applied to z at capital T, Tx. So I start at x at time t with initial value x and go to the final time. And this function then satisfies the Kolmogorov equation without drift term. Okay? So then we can have the following weak error representation formula. So the weak error can be written like this. There is first the initial error here. And then the main term is the expected value of this integral of the trace of this product of 3 factors. The first is the second derivative of the function u, the solution of the Kolmogorov equation, evaluated along a path of yh. And then here you recognize the error in the semigroup and q in the middle, and then we have a similar expression but with a plus sign and the adjoint. And this is proved by applying Ito's formula to u of yh of t and t, and the Kolmogorov equation, plus some delicate manipulations with the trace of products of operators. So then, if we apply it to the Cahn-Hilliard-Cook equation, we have these solutions. And there is no initial error here. And so we have to evaluate this integral of the trace, where we have the error operator fh here, which is bounded like this. So it requires some regularity, and we have to distribute that regularity, put some on q and some on this. And if you do that in the good way, you can prove an error estimate. But in order to formulate that, I need to say something about the trace norm. So the nuclear operators are denoted by L1H. Roughly speaking, these are the operators for which you can define the trace, like this, using an arbitrary Owen basis. And it's a Banach space with this norm here. And the connection with the Hilbert-Schmidt norm is that the Hilbert-Schmidt norm squared of an operator t is the trace of t star t, the symmetric positive quantity operator, which is equal to the trace norm of that. So the Hilbert-Schmidt norm is a symmetric thing. So the result is like this. We have a different condition on q now. It's essentially the same as the old one. I'll explain that in a moment. So again, with a parameter beta, which is between 0 and 1, and there is an alpha which should be positive with this restriction here. Then the weak error, when the test function g is c2 beta, twice differentiable with bounded derivatives. The function itself need not be bounded. It's of order h to the 2 beta under this condition. So that's twice the rate of strong convergence. Remember, under this condition here, we had strong convergence of order beta. Now we get h to the 2 beta. Of course, now beta has to be less equal 1 because we cannot get higher rate than 2 anyway for piecewise linears. Well, the comparison of these two conditions is that, remember, we had this condition of order beta, which is the trace of this symmetric thing, which can be bounded by the trace norm of this non-symmetric thing, and which in turn is bounded by the two operators, the two norms that occur here. So this condition is essentially the same as this. Okay. So actually this type of proof was first done by Arnaud Debuche and Jacques Printemps for the heat equation. And so we can say that we have generalized it to the Cahn-Hilliard equation, but also to the wave equation. Speaking about the wave equation, a similar weak convergence result was done at the same time by Erika Hausenblas. Okay, now let's return to the nonlinear equation. So here we have the full nonlinear Cahn-Hilliard-Cook equation written in mild form here. And so now the stochastic convolution and its finite element approximation are known. And it remains to study this equation here and its finite element approximation. Then we can start with a paper of D'Aprato and Debuche, where they prove existence of solutions of the nonlinear Cahn-Hilliard-Cook equation with polynomial nonlinearity. And briefly, I can explain what they did here. They assume that there is a common eigenbasis for A and Q. And they use a Galerkian approximation based on this eigenbasis, yn, in order to solve the equation for y. So yn converges to y in a suitable sense. And for example, there are basically three existence results: existence of solution in H minus 1 and and in H and in H1. So if I quote the result with the strongest regularity, y is in H dot 1, continuous, I'm missing a parenthesis here, continuous in time with values in H dot 1, provided that Q satisfies this condition here. Now compare that with what the condition we have for the stochastic convolution. We note that this means beta equals 3. So the stochastic convolution has regularity of order 3 under this condition, but y has only regularity of order 1. Well, the reason why this is so is that when you study the equation for y, of course they use energy estimates while we use this semigroup formulation. But anyhow, you have to take some norms of the nonlinear term, and WA is inside there. And when you take norms of this, you have to use Hölder and Sobolev inequalities, which will put derivatives on the ingredients, in particular in derivatives on WA. So even to bound the one norm, you have to use 3 derivatives here, essentially. Okay, so our goal, so this kind of regularity is not quite sufficient for convergence of the finite elements. So we want to prove more regularity and convergence estimates. Okay, so we want to study this. And in order to do so, we have to control the nonlinearity, which we assume is cubic. And so, for example, we need to take a norm of the nonlinear term A of f of u. That's the Laplacian applied to f of u. And for example, you can prove that this bound where you have u in the 1 norm squared and times u in the 3 norm. Or when you study error estimates, you have to look at differences like this. And then it turns out that this is useful. A bound for a Lipschitz bound from L2 to H minus 1, where the Lipschitz constant is controlled by the 1 norm squared. So it's useful to bound x of t and xh of t in the 1 norm to be used in such bounds. Okay, in order to do that, we introduce the energy functional. We have seen that yesterday. Here, f of u is a primitive of little f. It's a double well potential. In the deterministic case, this is a Lyapunov functional for the Cahn-Hilliard equation. So that you have that j of x of t is bounded by j of x of 0. However, in the stochastically perturbed equation, you feed something in, so this is no longer true. But what you can prove, and that was already done by Da Prato and de Biche, that under this condition here, you can prove that the expected value of j of x of t is bounded by c of t. So there is some growth. Same for the finite element process. And hence, you get the bound for the 1 norm, because that's included here. Okay, and the proof is based on applying Ito's formula to j of xn, the Galerkin approximation of the true solution or the finite element solution. However, we have generalized this result a little bit. First, we don't assume that there is a common eigenbasis of A and Q. And they also assume that there's a uniform bound of the eigenfunctions. And we also improved the growth to be quadratic instead of exponential. And most importantly, we get the same bound for the finite element solution. And in fact, this was actually the reason why we did these other improvements, because for the finite element equation, even if A and Q have a common eigenbasis, you cannot deduce that AH and QH have a common eigenbasis. So we simply had to find a different proof. Okay. All right. So now we have such a bound for the expected value of the H1 norm squared with quadratic growth in time. So we can put that in here, maybe. Well, we have this bound for the nonlinear term. If we take the expected value of that, we have to take the expected value of this product here, which is this product. And if you apply Hölder to get this, you see that the exponent is now 4, bigger than 2. So that just doesn't work. So we have to give up the idea of proving something in mean square. So instead we use Chebyshev's inequality to say that from this it follows that for any t and any epsilon, there are kt and omega epsilon, a subset of the sample space omega, with probability of omega epsilon larger than 1 minus epsilon, and such that we have this bound, which is epsilon to the minus 1 times kt, where kt is this growth. And this holds uniformly on omega epsilon and a specified time interval. So now we can work pointwise on omega epsilon. Okay, well, a large part of the technical work will have to be done on proving error estimates. And that can be done for the corresponding deterministic linear Cahn-Hilliard equation. So here I've written the deterministic linear Cahn-Hilliard equation. Linear means that instead of f of u, I have written a fixed function g here, and the corresponding finite element problem. And then we prove a time derivative free error estimate. That goes like this. So the error in this finite element problem is of order h squared. That's the optimal order for piecewise linears. And it uses a second regularity of second order for u in this sense with a log factor in front, and for v in this sense. V is the second function in the equation, the chemical potential. Okay. So this does not involve any time derivative, which is important because we will have to bound these in terms of the given data, the initial value, and the forcing g. And without taking derivatives, time derivatives of g. Because we will use this with g of t being f of x of t, which has no time derivative. And in which case, if we put g equals f of x of t here, the solution u will be exactly y. And the corresponding finite element equation here will be a new auxiliary finite element solution, which has f of x here, not f of xh. So the proof of this is different from the other, which was for the approximation of the semigroup. In that case, we are allowed to put derivatives on the solution because it's the semigroup, which is smooth in time. Okay. Well, if we put all these together, we are able to prove regularity of order t, of order 3, pointwise in time, and in omega epsilon. And also an error estimate of order h squared on omega epsilon for every epsilon and for every t. However, it blows up when epsilon goes to 0 and t goes to infinity. But it has the optimal rate. However, if you combine the fact that this goes to 0 when h goes to 0, and omega epsilon has a large probability, you can actually prove this strong convergence estimate in mean square. But the rate will be very small, because here we have used a Gronwall argument. So this constant grows exponentially with this quantity here. So this is recent work together with Michi Kovac and Ali Mesfouroush. And it was part of his PhD thesis, which was presented 2 weeks ago. Okay. That's all I had to say. Thank you very much.
Questions? Yes.
So do you expect to improve the beta if you use higher order finite elements?
Yes. So, for example, for in the linear case, where the strong convergence.
Yeah, the result you showed earlier. You said that.
Actually, we proved that for arbitrary order, in fact. So if you have finite elements of higher order than piecewise linear, quadratic or cubic, then you get the corresponding higher rate of convergence. For the weak, I don't know. At least we haven't done that. We have only studied piecewise linears. Here, of course, the regularity is of order 3, which is in the nature of the proof, because the already under the same assumption on Q, W has regularity of order 3. So this is what we get from this proof. While here we have second order convergence, so that we have actually proved the cubic convergence also for if the finite element is of a cubic one, but of cubic order. But it's since we don't get any rate here, we didn't actually write that down in the paper.
More questions?
You use the function capital F, which goes quadratic. Would it be possible to replace capital F by another energy which goes faster or is non-smooth?
Probably yes, because the essential thing is that it's positive, bounded from below, so that you have the corresponding energy. Yes.
All right, no more questions? Let's thank our speaker one more time.